Very good evening to all of you. So thank you for joining us today.
Good evening, sir.
Yeah, so today we have this session on wide bandgap semiconductor simulation using Synopsys Sentaurus TCAD software. So my name is Deepak Upadhyay. I am a principal application engineer at Integrated Microsystem, Delhi. So today we are going to explore how Synopsys Sentaurus TCAD help us to explore the wide bandgap semiconductors that used in the advanced power electronics devices. So without any further delay, let me start this session. So firstly, I will give you some brief presentation about this tool and the features that we have under the Sentaurus ticket, and after that we will go to the live demonstration. And after the live demonstration, we will have a question answer session. So in that time, you can ask your queries. So if you talk about the quantum ATK, so this quantum ATK is an atomic scale materials and device modeling tools that will help you to simulate large scale materials. So this quantum ATK is ideal for exploring quantum mechanical properties like electronics, structure, or electrical, thermal, mechanical. So all these things at the atomic level you can do by the quantum ATK software. So alongside the quantum ATK, we have the Synopsys Sentaurus TCAD, our next generation simulator to design and optimize the semiconductor device. And it supports a wide range of materials and physics models that make it suitable for both current and future technology. Synopsys also offers a complete VLSI package. So we have the front end and back end tools, and we also have the custom compiler for the analog and mixed signal designs. So this end-to-end flow from RTL to verification, physical implementation to sign off will ensure the seamless integration, and it provides the higher accuracy. So today we have this session on Synopsys Sentaurus TCAD. So we will focus on this TCAD software only. So Sentaurus is the industry-leading suite for technology computer-aided design tools that enable the simulation of both fabrication process and the device physics. So it supports both the simulation process like etching, oxidation, implantation. So all these things you can do by the process simulator. And we also have the device simulation which help to analyze the electrical behavior under various biasing conditions. So the goal of this Synopsys Sentaurus ticket is to bridge the gap between the manufacturing and the electrical performance that will allow the engineer to optimize the design before the fabrication. So this Sentaurus provides the detailed insight into how materials and structure we have that will help to reduce the development time and cost. So here you can see I have exported the raw data that is from the device simulation. So it is a drain current versus drain voltage, and we have also exported the special distribution of electric field and the doping concentration. So these visualizations are very essential for validating the design assumption and understanding the device behavior at the microscopic level. So here you can see we are going to explore the full breadth of this Synopsys TCAD product family. So this suite is modular that covering every aspect of the semiconductor simulation. So starting at the top, we have the Synopsys Quantum ATK for the atomic scale material and device modeling tools. So it comes with the device that is called Virtual NanoLab. So this virtual envelope will help to create a restructure. You can also do some modification, manipulation in a restructure, and then you can go for the job simulation settings. So it also comes with the Sentaurus material workbench that help you to simulate your material at the atomic scale and that you can export as the input in the TCAD simulation. So here you can see this is the complete flow for this Synopsys Sentaurus TCAD where we have the process simulation. So in the process simulation we have the Sentaurus process that will help you to generate a structure based on the fabrication steps. And if you want to optimize that structure, then you can go with the Sentaurus topography. And here we have the process simulation. So for the process simulation, we have the Sentaurus Process Explorer, which help you to analyze and optimize the process. Now, structure editing is handled by the Sentaurus structure editor that will help you to create or structure in 2D and 3D view. And device and interconnect simulation is handled by the Sentaurus device, Sentaurus interconnect, and the Raphael effects, which help you to analyze the electrical and also parasitic effect of the compact model by the Raphael effects, which help you to simulate the resistance and capacitance of the devices. So it also comes with the GUI that is called Sentaurus Workbench. So Sentaurus Workbench is the central tool that help you to integrate all the tools like process simulator, device simulator, structure editing. So all these things you can integrate in the Sentaurus Workbench, and you can also fire it off by the Workbench. And once you fire the job, you will get some output that you can visualize from the Sentaurus visual, and that help you to interpret the data in 1D, 2D, and 3D view. Now here you can see we also have the ticket to spice level simulation like grand V, mystic, and the random spice simulation. Now, if we talk about the Sentaurus modules, so in Sentaurus we have the four modules like Sentaurus Process, Sentaurus Device, Sentaurus Visual, and Sentaurus Interconnect and Explorer. So the Sentaurus process is basically help you to create or restructure by using the fabrication steps like etching, oxidation, implantation. You can also define the dopings. And once the restructure is ready, you can take the device into the Sentaurus device simulator. So this Sentaurus device simulator is called ES device that will help you to simulate the devices, and then you can analyze their electrical, optical, and thermal behavior. Now, once you do the simulation, you will get some output, and that you can visualize from the Sentaurus visualizer, and this visualizer will help you to interpret the data in 1D, 2D, and 3D view. Here you can see we also have the Sentaurus Interconnect and Explorer that will help you to parasitic extraction and the layout designs. So this workflow typically follow four steps: structure creation by the structure editor, and then we have the Sentaurus process, then we have the Sentaurus device, and then we have the Sentaurus visual. So this modular approach allows you to focus on the specific aspect of the devices, whether you are working on the FinFET, SFET, CMOS image sensor. So these modules provide the flexibility and depth that is needed to simulate the complex semiconductor behavior. So the process simulation is the foundational capability in the Sentaurus ticket that enable the user to model the semiconductor fabrication steps in 1D and 2D view. So this slide highlights the feature of this process simulation that also integrate the 3D geometric models for deposition, etching, and patterning, and also it comes with the adaptive meshing that ensure the simulation grid adjust dynamically to change in the geometry and the species concentration that will improve the accuracy. You can also define the custom models by the API that will allow for the tailored simulation. And it also comes with various advanced physical modules like analytic and Monte Carlo implantation, diffusion, laser and flash handling, kinetic Monte Carlo, mechanical stretching, and oxidation and silicidation. So this capability allow engineer to simulate the real world fabrication condition with the high fidelity. And here you can see we have exported the output from the process simulator by the kinetic Monte Carlo, mechanical stress, adaptive meshing, and the oxidation. So this structure will show how this model capture the complex physical phenomena by the process simulation. Now, if we talk about the structure editor, so structure editor is a powerful tool for creating and manipulating the device geometry in both 2D and 3D. So it also comes with the graphical user interface and also scripting capability for the advanced user. And you can also perform the geometrical operation like you can define the doping profile analytical, and it also provides the direct interface with the meshing engine. So this flexibility allow for the precious control over the device architecture. This is very critical for the accurate simulation results. And this editor support the complex structure like DRAM, CIS, image pixels with the micro lenses, through silicon wire structures. And here you can see this is the GUI of this structure editor that will help you to create a structure from the scratch. So you can go with the structure editor, and if you know the scripting, here you can see you can also write a TCL scripting, and then you can easily create a device. So in the structure editor, we have the various kind of materials that you can go from the material section, and once you select the material, you can go with the draw, where you can go with the automatic automatic coordination, and you can also go with the exact coordinate point that will help you to define your accurate device structure. Now, if we talk about the Sentaurus mesh, so Sentaurus mesh is dedicated meshing engine within the TCAD suite that help you to design and generate a high quality 2D and 3D mesh for the semiconductor simulation. So it support axis aligned and boundary confining mesh creation like triangle and tetrahedral structure, as well as the tensor product meshing for the structural grid like rectangle and the cuboid shape. And it also allows the flexibility to ensure the compatibility with the various simulation solvers like the box discretization and the finite difference time domain methods. And this here you can see we have exported the data for the Sentaurus mesh. So we have also done the meshing by using the different kind of meshing by the axis align and the boundary confinement methods. And you can see this is the GUI that will help you to view the meshing. You can go with the material, or you can enable, you can disable the particular materials. You can define the regions as well, and you can also disable and enable the line and particle in the devices. Now, if we talk about the Sentaurus device simulator, so this device simulator is a core module for the analyzing the electrical behavior of these semiconductor devices. So it supports multi-dimensional simulation in 2D and 3D. So it supports the multi-dimensional simulation both 2D and 3D, and it also covers a wide range of materials including silicon, germanium, silicon, gallium, and also go with the silicon carbide, third and fifth compound materials. You can also go with the germanium, and you can also go with the gallium nitride, indium phosphide. So all kind of materials you can easily take for the device level simulation. It also comes with the various transport methods like drip diffusion, hydrodynamics, thermodynamics, and Monte Carlo simulation. And it covers a wide range of advanced physical models like stress dependent mobility models, field dependent mobility model, temperature dependent mobility model, quantization, and random looping effect. You can also go with the circuit mixed mode signal analysis, harmonic balance, and it also covers various variability analysis and many more advanced physical models for simulating a wide range of devices. Like you can go with the FinFET, wide effect, you can go with the NAND flash, CMOS image sensor, UMOS devices. So any kind of a complex structure, you can easily go with the advanced physical models. Now, if we talk about the Sentaurus workbench, so Sentaurus workbench is the central framework that tie together all the TCAD modules into a unified simulation environment. So it offers a project management, design of experimental tool, and also the optimization workflow, and it also considers the job framing for the parallel simulation. So this integrates the ticket data visualizers that help you to interpret the result within the interactive plot. And these results here you can see how you can go with the any kind of devices by the S device you can go with the S process. So it comes with the project management that will help you to define any stress project. You can also go with the example that comes under the center surveillance. Now, if we talk about the Yes Visual, so Yes Visual is the visualization modules within the Sentaurus TCAD that help you to design and interpret the simulation visual through interactive graphical representation in 1D view, 2D view, and 3D view. It also comes with the graphical rotation that you can rotate your materials and output data in X, Y, and Z. You can also do zoom in, zoom out. You can also go with the height and enable and hide of the materials and particular region as well by the Yes Visual. So Yes Visual is a very easy to use graphical user interface, and it also provides the TCL scripting for the advanced user. So if you want to automate the visualization for the advanced application like for the publication papers and things. Now we talk about what is band gap and why it matters. So band gap refer to the energy that is required to excite an electron from the valence band to the conduction band. So it means it is a energy barrier that electron required to overcome the electrical conduction, and the size of the band gap that has significantly implication on the device behavior. Suppose if the band gap is large, then the semiconductor requires a higher critical electric field to initiate the impact ionization, and this process is called avalanche breakdown. And this phenomena occurs when carriers gain enough energy to generate the more carriers, and that is potentially leading to the device failure. So because of the larger band gap, it requires a higher energy for the ionization, and devices with this wide band gap material that exist a higher reverse voltage capability. So the breakdown voltage of the device is given by the formula 1 by 2 into drift width and into critical electric field. So additionally, the large bandgap materials that can operate at a higher temperature, since more energy is needed to cause the ionization, and this makes them highly suitable for higher temperature and higher power applications that result in the reliable and efficient performance even under rising condition. Now let's see why the bandgap semiconductor devices are gaining so much attention in the modern semiconductor applications. So WG devices offer lower on resistance, which make them uh, which makes them, and it can conduct the current more efficiently, reducing the energy loss, and also it also provides the faster switching speed and lower switching losses, making them highly suitable for the application that require rapid and just a second. बस So sorry for this disruption. So along with this, it also provides the faster switching speed and lower switching losses. That is making them ideal for the suitable for the repeated on-off cycles such as power converter and the inverters applications. So another significant advantage. So it also provides the better thermal conductivity that help to dissipate the heat efficiently, and that ensure the device remains stable under heavy load. So wide bandgap devices are also smaller in size and for the same voltage rating. This allow compact designs, and in many cases they are also more cost effective due to the higher efficiency and the smaller footprint. So they are high reliable and durable with the excellent high voltage blocking capability. This is very critical for the power electronics application. So this advantage makes a wide variety of semiconductor devices ideal for a wide range of applications like power electronics, electric vehicle, energy resources, motor, drive, power transmission, and the consumer electronics, where efficiency, reliability, and the compactness are very crucial. Now, if we talk about the four hexagonal layer of Schottky diodes, so this is the device that we are going to demonstrate in the live. So now if we talk about their applications, so it is it provides a higher temperature and the higher power applications. So thanks to the large bandgap of the silicon carbide devices that allow reliable operations and at the elevated temperature. They are also used in the high frequency rectifier because of the fast switching capability as well as the switching power supplies where efficiency and the thermal system stability are essentials. So another growing application in the electric field charging system where the compact high efficiency power conversion is required. Finally, they are also used in the solid state RF and the microwave circuits and taking their advantage of their low forward voltage drop and the fast switching speed. Now, if we talk about the working principle of this four hexagonal layer of Schottky diode, so Schottky diode, we create four hexagonal layer of Schottky diode create a metal semiconductor junction rather than the conventional PN junction. So the Schottky barrier at the contact surpasses the binary carrier injection. This is making it to reduce the storage time and also allow the very fast switching speed. And when a uh, forward bias is applied on the devices, so it injected the current flow from the conduction band to the valence band. And while reverse biasing helps us to diodes that can achieve the fast breakdown and also the high voltage blocking capabilities. So this is the working principle of this, for example, of Schottky diodes. Now this is the template that we have to follow for simulating the devices by using the Synopsys Sentaurus TCAD. So first, starting with the overview, we use a template-based TCAD setups that specify the four hexagonal layer of Schottky diode, and this ensure that all the key materials parameters like mobility models and physical models that are properly confined for the wide bandgap accuracy. Now, we generally focus on two approaches. First, we are going to simulate the forward IV current, and then we are going to simulate the reverse breakdown current. So, this forward IV characteristics will help to study the turn on behavior and also the barrier height and the conduction efficiency. And this reverse part will help to evaluate the diode blocking capability and also the avalanche behavior and the electrical distribution. So here you can see this is the steps that we need to follow. So first we are going to use the structure editor for creating the structure, and then we will define the meshing for the better accuracy. And once your structure is ready, we are going to simulate our structure by using the device simulation, where in the device method we are going to execute the various physical phenomena for simulating the IV and their breakdown capabilities. And in the last, we will use the S visualizer for visualizing the results. Now, if we talk about the model requirements for Schottky diodes, so for the wide band gap, Schottky diode has an extremely low intrinsic carrier density, which significantly increase the sensitivity of the solution. So this means the device model require enhanced numerical accuracy of for the final mesh and stable physical models that avoid the convergence issue. Next, we have the Schottky diodes. In that, we are going to simulate the current transport that is dominated by the tunneling through the Schottky barrier. And this is not a simple harmonic process. So we are using non-local models for the exact transport models for the Schottky diodes. And here you can see we are going to execute these three methods for simulating or Schottky diode very efficiently. So first we have the non-local mesh construction that will help to capture the grid and the electric field curvature at the metal semiconductor interface. Then we have the energy resolved or tunneling integration that allow the simulation to capture the tunneling probability across the full energy spectrum. And then we have the various lowering models which account for the original force lowering and also the high field effect that is typically in the silicon carbide devices. So here you can see we have simulated this four hexagonal layer of silicon carbide Schottky diodes, and we have simulated their forward bias current. Now, if we talk about the modeling approach that we have in the Synopsys Sentaurus TCAD for modeling the SiC Schottky diodes. So it comes with the various transport models for the deep diffusion models. Like it will help you to accurately simulate the diode IV and the CV characteristics. It also comes with the Schottky contact models that involve the tuning the metal work function, and that you can also define some kind of doping by using the nickel and titanium that will match the Schottky barrier height and turn on voltage. So it comes with the various mobility models like field dependent, temperature dependent, and also the electric field dependent mobility behavior. And it also comes with the various recombination models like SRS, agar, impact ionization that will help you to predict the carrier lifetime and the high current effect and the breakdown voltage. It also comes with the incomplete dopant ionization models. This is very critical for accurately determining the drift layer across the carrier concentration in the silicon carbide devices. Now it also provides the various advanced reliability and the roughness analysis that cover the radiation damage modelings that help you to simulate the heavy ions strikes, displacement effect, and resulting in the leakage radiation at the junction. And now it also comes with the self-fitting and the thermal runway analysis, which is using for the electrothermal simulation that will help you to evaluate the power over stress condition and risk of the single event burnout. Now, if we talk about the wide range of applications that we can cover by using the Synopsys Sentaurus TCAD software. So, whether you are working on the FinFET CMOS devices and planar CMOS devices, so you can also utilize this Synopsys Sentaurus TCAD for the logic application. So, it supports the CMOS, FinFET, NanoFET, TunnelFET, and even various emerging technology as well. And in the memory application, you can go with the NAND, NOR flash, DRAM, 3D NAND, PRAM, and also screen transfer torque time. And in the power application, you can go with the silicon IGBT diode, ZLD MOS, VCD, silicon carbide, gallium nitride. So all this kind of complex structure you can easily simulate for the power application devices. And if you talk about the analog and RF capability, that include the silicon germanium hydrogen bipolar transistor, gallium arsenide HEMT application, gallium arsenide SVT, gallium nitride HEMT, and silicon carbide metal or metal semiconductor field effect transistors. And if you talk about the optoelectronics application, so you can go with the CMOS image sensors, charge coupling devices, photo detector, silicon solar cell, and also third and fifth solar cell devices. So this is the wide range of application where you can utilize this Synopsys Sentaurus TCAD. So thank you for listening to this presentation. Now I would like to switch on the demonstration part. And in the demonstration, I will show you how we are going to create any kind of structure from the space and how in actually in Sentaurus TCAD there are two approaches for creating a structure. So let me open my software. So here you can see I have already taken. Yeah. So this GUI is called Sentaurus Workbench. That is basically a front-end tools that integrate all the TCAD module into single GUI. So you can integrate the process simulation, you can integrate the device simulation, you can integrate the yes visual, you can also integrate the structure editor. Now here you can see it comes with the list of a project that will help you to start from this scratch, and you can also create your own project by selecting this project option. Now we are going to create our structure first. So for the structure creation, we have the structure editor. So here you can see this is the structure editor GUI that will help you to create a structure from the scratch. And here you can see it comes with a list of materials that will help you to select for a particular application. So I am going to create a four hexagonal layer of silicon carbide Schottky diode. So for that I need to select the 4H SiC materials. So let me select. Yeah, here you can see we have the silicon carbide and four hexagonal layer. 6 hexagonal layer. So, and if any material is not present in the material section, then we have the Synopsys quantum ATK that will help you to export the material, and you can utilize the TCAD as input. Now, this silicon carbide is a leading candidate among the wide bandgap semiconductor materials for the next generation for semiconductor devices. So, we have selected silicon carbide. Now, the next step is to select or dimension of the devices. So, for that, we have to select the view, and in the view, here you can see we have the ZY mode. So, in the ZY mode, we have the 2D mode and we have the 3D mode. So I am going to create a 2D structure of silicon carbide. So I would like to select the 2D mode, and once you're done with the selection, you can go with the draw. So in the draw, you can see if you know the exact coordinate point, then you can go with the exact coordinate. And if you want to go with the random, then you can go with the auto region naming. So I would like to disable this auto region naming, and I would like to go with the exact coordinate point. So if you know the structure information, then you can easily design. And if you also know the script, then you can also write the teacher scripting here, and then you can easily design a device. Now, once you select all the material and also the dimension of the devices and the exact coordinate, then here you can see we have the shape of the device. So I am going to select the rectangle shape. Now you can see the rectangle shape has been selected, and here you can see this is the arrow. So we are going to draw a rectangle shape, and here I would like to define the exact coordinate point in the x and y for the silicon carbide devices. So first, I would like to design SiC 4H substrate material. So for that, I would like to define the region. So I would like to take from 5 micrometer to 15 micrometer in the X, and in the Y, I would like to take 0 to 5 micrometer. So once you've done, you can select the OK, and here you can see we are going to define the region name. So this is our substrate region, and here you can see we have taken SiC materials, and this is my substrate. So once you define the region name, you can select this OK, and you can go to this search. Now you can see we have designed a silicon carbide 4 hexagonal layer of substrate material. So once you've done, we are again going to define the EP layer. So for that, I would like to select this same materials and then go with the rectangle shape. You can draw and then define the exact coordinate point. So for the EP layer, I would like to deposit the EP layer at top of the substrate. So for that, I would like to define 0 to 5 micrometer in X, and in the Y 0 to 5. So once you've done, you can go with the OK. And here you can see we are going to define the region name. This is our EP layer. Now then select the OK. So you can see this is our substrate, and here we will do PN plus region, and in the EP layer we will go with the heavily ENDO. Now we have created two layers, and now we are going to deposit oxide layer at top of the EP layer. So I would like to select the oxide layer. Here you can see this is the oxide material, SiO2, and we are going to deposit. And here I would like to define the exact coordinate point. So from -1 to 0 in the X, and then in the Y I would like to define from 3.2 to 5. This is our oxide layer, and then select the OK. Now you can see we have deposited the oxide layer at top of the EP layer. So once you've done with the material selection and material deposition, then you can go with the edge define. Like you can define the top of the Schottky contact, ohmic bottom contact. So for that we are going to select the edge, and here you can see I would like to define the vertex. So if you want to define the vertex for top of the like substrate and bottom of the substrate, then you can go with the edit 2D tools, and you can go to the add vertex. Now we are going to add the vertex, and here you can see I would like to take the point from 0 to 5, sorry 0 to 3, then OK. Here you can see here it will create a dot point. Now you can see. And same, I would like to define for the bottom ohmic contact. So for that, I would like to define 15 to 5. Then select OK. Here it will generate a dot. If you go with the 3, you can see that it will generate a dot. So I would like to go with the 5. So I would like to define the again 15 to 5 micrometer. So in this case, the total length of the substrate is 10 micrometer and the length of this EP layer is 5 micrometer. Now we are going to define the contact. So we can go to the contact set. Here you can see here we are going to define the contact name and then S color. So this is the RGB, RG and B. So first I would like to define top of the short key contact. So this is the short key contact with the red color. Then set. Here you can see this contact has been set. Again we are going with the bottom. Now this is the bottom and this is the ohmic contact. And then for the ohmic contact, I would like to go with the green. So this is the 0 and here I would like to define one RGB and then set. I can see two contact has been selected. Now I'm going to click on this close. Now if you want to activate this contact, so you can go to the vertex and then here you can select top shortly contact. You can select this arrow and now you can click on here. Sorry, we have to select the yes, yeah. Now you can see this orange one highlight the top of the shortkey contact and we are going to set it. So if you want to set, you need to click on this set contact, then it will float a red color. Now you can see. Similarly, we are going to select the bottom ohmic contact. So let me select, yeah, and then you can go with the set contact. Now you can see I think we have added with the, sorry, we have selected top shortly contact. So here you can see we have the redo and undo option as well. So I would like to select the undo and here I would like to select the bottom ohmic contact and then select and go to the set contact. So you can see it will float a green color. Now we have done with this structure building. Now we are going to define the mesh. If you want to define the doping as well, you can go with the device, constant profile placement, and here you can see. First, we can select the region. We can go with the constant profile definition, where you can also define the species, their concentration. So once you've done, so I'm not going to define here because I have already created a project in the workbench. Now, if you want to define the meshing, here you can see this is the meshing. We can go with the line, we can go with the rectangle, polygon. So, if I select the rectangle and let me select this one. So this is the rectangle one, and I can see. So this way we can define the meshing. Here you can see this is the region. So I'm going with the default parameter now. Select the OK. So you can see the mesh has been defined. So this way we can also define the mesh. If you want to define the mesh for any particular region, if you want to define the meshing here only, then you can select the region and you can go with the build mesh. You can see this is the build mesh. Now here you can see it has generated this script. And if you copy this script and paste in the workflow builder, so let me open the workflow. Here you can see this is our workflow. Now let me go with the examples that I have already created. You can see this is the silicon carbide, and it also comes with the software itself as well. So you can see this is the Schottky diode, and here you can see this is our device. So I have already pasted the command. You can see this is the command option. Now you can see the same command I have already pasted. So I am going to copy. I can see the command has been copied, and I am going to create a new project from scratch. So for that, I would like to select this one. Here you can see. Oh, just a second. Yeah, here you can see there is no tool added. Now we are going to add the tool and we are going to add the command as well. So first you can select this one, right click, go to the add option, and here you can see we have the tool. So in the tool we have all the tools like the structure editing, yes process, yes device, so all the tools we have. So just we have to select, go with the OK. Now you can see this is the yes device and then select the OK. Or yeah, yes, that has been added here. Now you can see we are going to add the command. So you can select the edit input, go to the command. Now you can see this is the SD DBS command. So I think I have already created this one. So it is showing the same. So once you've done, and here I am going to define the length and also the thickness of the device. So if you want to define the thickness and doping value, then you can just click here, right click, and go to the add parameter and value. So in the add parameter and value, I am going to define the thickness and also the length of the device. So here you can see I would like to define first the doping. This is the AP doping, and you can also define their value. So here I'm going to define the list of value. So this is around 1E, 1E50. Now you can see this value has been floated here, and just you can select this OK. Now you can see e-doping has been added. So here we are going to add the parameter. In the properties here you can see we have the default value and then select the OK. Now if you want to define the thickness of this device as well, so I am going to select again SDE, add parameter and value, and here I am going to define EP thickness. Just this is the EP thickness, and here I am going to define 5 micrometer. Now you can see. So we have defined the doping and we have defined the thickness. Now once you've done, you can go with the simulation. So just you can select the SD and go with the simulation. I can see we are going to simulate, then select this OK. So once the simulation completed, it will generate a device structure with the doping and the thickness. Now if I show you the information about this, I can see this yellow color is so the simulation has been completed, so we can go with the result. So if I show you the node information, so this is the number of step 3, node is a 0. Yeah. Now let me show, just a second. One 15. This is the okay. Now if I show you the output, so let me open the S visualizer. So here I'm going to load the S visualizer. So just a second. And then yes visual. So by using the yes visualizer, we are going to load the file. Here you can see this is the open, and here you can see we have the project. Now you can see this is the nmos.tdr file. We are going to open it. I can see. So this is the device that we have created, that we have simulated actually. Now let me go with the previous one that I have already simulated. Here you can see this is the Schottky diode. Now you can see. Here we have defined the doping thickness and then we have defined the device. Similarly, you can go with the add option. You can add any device tool. So I am going to add the device again. So let me show how we are going to define the command as well. So just select the add option. Now you can see the CS device has been added. Now if you want to define the script as well, here you can see I have already tested the script here in the command section. Now you can see this is the script. And if you want to write this same script by using the yes wizard, so just you can right click, go with the edit input, and here you can see this is the yes device wizard. That will help you to write your script. And if you are like expert in writing the script, then you can go with the edit command as well. Now you can see it cover a wide range of physics for different kind of application like for electric devices, two-terminal devices, three-terminal devices, four-terminal devices. You can also go with the advanced devices, power devices, memory and logic devices, heterojunction devices. And here you can see we have the physics that is for the wide bandgap devices. So we have created silicon carbide. So we will go with the SiC devices. You can go with the next. And here you can see we have the power efficient devices in 2D, and here you can see this is the four hexagonal layer of silicon carbide and MOSFET. So I am going with this one. Go with the next. And here you can see these are the various static characteristics that we can define. So I would like to go with the IDVG, and we will also go with the breakdown analysis. So first I'm going with the IDVGS, then go to the next. Here you can see there are some basic parameters that we have to define before the simulation. Like you can see we can go with the transport models, we can define the ambient temperature, we can define the band gap narrowing methods. You can also go with the mobility models, recombination and generation, and isotopic models. You can also go with the dopant incomplete ionization. So these are the parameters we have to define. So once you're done with this settings, you can go to the next. And here you can see this is the numerical parameter substrate. So we are going with the device dimension related to the 2D substrate, and we have enabled this one. So I am going with the default one, and we can also go with the number of threads for the parallel execution of the script. So once you done, you can go with the next, and here you can see. So this is the script that has been generated by the result. Go to the finish. Now you can see. Let me show the command. So you can see this is the command that we have generated by the SVR tool. So this way we can also create a script from this space. And once you've done, you can go with the simulation. Just select yes, and you can select this OK. So this way we can fire this off. And here you can see I have already simulated this off. We can also I have already defined the work function as well. This is the 5.1 micrometer. Now I am going to show the result for this SiC Schottky diode. So let me open the S visualizer, and here you can see this is my project location. So let me open the file, go to the open, and here you can see I have Schottky diode, and in this here you can see first I have EN4. This is the node 4, and this is the band.tdr file. So this will this store the information about the structure. Yeah, you can see. Let me close it and open it from scratch. So this one is from default parameter that we have simulated by the SVChat. Now you can see this is the device that we have created by the structure editor, and here you can see we have simulated by the workbench. Now here you can see if I show you the materials, so you can see this is the silicon carbide material. We can hide. Oh, just a second. Let me select this one. Yeah. Here you can see this is the silicon carbide. Here we have the top of the Schottky contact, and we have the bottom of the ohmic contact, and this is the oxide. Now if I load the meshing file, so let me load. You can see this is the node 4 mesh.tdr file. Now you can see we can define the mesh as well. So you can see this is the doping concentration. Now here we have the meshing that yeah, now you can see the mesh has been added at the silicon carbide layer, and after the interface oxide. And let me show you the junction line while disabling this one. Yeah, here you can see we have the junction line. Let me maximize it. Yeah, you can see this is the junction line, and this is the contact, top of the Schottky contact, and this is the bottom of the ohmic contact. And this is the doping concentration that we can also visualize. You can also go with the boron active concentration, like you can see. So these features you can usually upload once you done the simulation. Now let me load this one, uh, the IDVGS. So for that, this is the, let me show the node information. This is the node 12, and here you can see. Let me go with the file open. And here you can see we have the node 12 or discussion.plt file, and here we have TDR file. So if you want to show the structure only, then you can go with this TDR file. And if you want to plot the graph, then you can go with the IVM12. Now you can see here we have the data. This is the IV for the top sort key. So I would like to select the top sort key, and then I would like to select there. Here you can see we have the different options for plotting the data. So we have the outer voltage, inner voltage, positive Fermi potential. So all this you can select and you can plot at the x-axis and y-axis. Now I would like to select the top of the sort key, and here I would like to define the inner voltage at the x-axis. So you can see I have selected. Now I am going to select the total current y-axis. Now you can see the same plot I have already shown in the presentation. So this is the forward IV direction. You can select and delete. Yeah, here you can see we have the data VV, and here we have the top sort key, bottom OMI contact, and sync step. So for I'm going to select the top sort key and their inner voltage at the x-axis, and then top sort key their total current at the y-axis. Now you can see. So this is the breakdown analysis graph for this four hexagonal layer of a Schottky diode. So this way we can work on the diode application as well by the Synopsys Sentaurus TCAD. So you can also cover a wide range of applications. Like you can see, you can also go with the gallium nitride IGBT, and you can also go with the FinFET devices as well. So I have already shown how we can create a project from this stage. So this is all about from my side for this topic, shortly out for this wide bandgap semiconductor simulation. So if you have any query, you can let me know. I will try to help you. Now this session is open for the Q&A.
Hello, sir. Good evening.
Evening, sir.
Yes, please.
Can you hear me?
Yes, yes, please go ahead.
Sir, good evening. This is Sriram. Actually, you told that if there are no materials, new materials are not there, now you can get it from quantum ATK, right?
Yes, quantum mechanism, right.
Uh, how can we measure the data from quantum ATK to this central speaker?
So as you know, in the like a central ticket for the materials application, we have to define their work function, their band gap value, their refractive index value. So all these value will export from the quantum ATK, and that and that we can define in the decade. Suppose you are going to define, you can go with the command, and first
Yeah,
you have
yeah,
to add the
that I
material in
understand.
the yeah.
Yeah, that I understand. But uh, uh, whether these parameters are already defined in ATK or we have to calculate by doing the
So
efficiency.
we have to calculate by the quantum ATK. So let me open the quantum
Okay.
ATK as well, so that you will get the information how we are going to calculate. You can also work on the new material as well. And I think suppose you want to create a MOSFET, and in the MOSFET you want to create MOS to graphene based channel materials. So in that case, what you can
Okay.
do, you can go with the quantum ATK. Just a second.
Hmm.
And then we can let me open this UI. Then it will be more clear.
Yeah.
Even quantum ATK is also useful for creating and simulating the devices as well at the atomic scale. But if you want to go for the microscopic level, then you can go with the Synopsys Sentaurus TCAD.
Okay, fine.
Yeah. So this UI is going to open. You can see this is the UI for the quantum ATK. So in the quantum ATK, we have a tool that will help you to create a structure from this scratch. So you can work on any material. So if you know their like lattice information, like their ABC value, their and also their like front phase center, cubic structure, what is cubic structure, tetragonal, hexagonal. So if you know the latest information and they are like atoms and their fractional coordinate point, then you can easily design a new material by the quantum mechanics. And then you can go with the simulation by the various method like the density function theory, semi-empirical, classical force field and machine and force field. And for the devices, we have the non-equilibrium Green function method. So once you done with the calculator settings, then you can go with the like analysis parts. Like if you want to find out their band gap value, then you can go with the band structure simulation. If you want to find out their mobility value, then you can go with the mobility analysis. If you want to find out their work function, density of the state. So all the workflow we have under the quantum data. So thus you have to calculate by the quantum ATO, and once this simulation completed, then you can go with the exporting the data from quantum ATO to the TCAD that will act as the inputs.
Yeah, yes, sir, yes, sir. Actually, the thing is, the results from quantum mechanics is the atomic level, right?
Yes, atomic level.
Excuse me, sir. Sir, I want
That's the
to.
problem which I'm facing because we have to map these to micro level and nano level differences. That's what I'm asking. Once we perform the DFT simulations or device simulations or non-equilibrium simulations in the quantum ATK, then what is the result we have to take from that, and how can I incorporate that with PCAP?
So in quantum ATO, like we have the various export options. You can export the data in the text format. And as you know, the Sentaurus TCAD also support the text format. So
No,
just you
no,
can take the value
yeah, yeah, yeah,
and
yeah.
you can define.
Uh, yes, sir. Actually, the output is .htf file, right?
So we have the export option as well, sir. So we have the like XYZ format. You can go with the text format. You can go with the image format. So once you done with the export option, then you can integrate with the center ticket. See, direct integration of the HDF file is not possible from quantum to ticket. So we have to export our data. So here you can see, let me show. Suppose this is the optical
Mm.
spectrum that I am going to open. And if you
Okay.
want to like export the dielectric constant value, I can say this is for the real part and this is for the imaginary part. So this is
Imaginary.
the
Oh,
export
fine, fine.
option. Yeah, this is the imaginary part. Now you can see this is the export option, and here you can see we have the text format. So we have to export. Let me see. This is the dielectric constant, and then save. So yeah, this is the desktop. Now here you can see this is the dielectric value. And these value we can easily integrate with the center ticket. So just we have to copy paste for the material. So first we have to create a directory in the material section for that particular materials, and then we can go with the importing the file in the ticket.
Okay, okay, thank you. Sir?
Sir, I want to ask you something.
Yes, please.
Sir, I want to include a material that is not available in Centaurus tool. What is the procedure
So
for this?
the same procedure I have already
Okay,
suggested
sir.
to Professor. I think, yeah.
Okay, sir.
So this is the same way you can integrate.
Sir, good evening, sir.
Yes, sir, please.
Sir, good evening, sir.
Yes, good evening, sir.
Means there is any example regarding to the thermal runaway, which is known as a single breakdown event in the centers.
Which one, sir? Can you repeat again?
You have shown the slide, no, sir, regarding to the single event breakdown,
Yes, a single event burnout. Yeah,
burnout.
by
So
the radiation effect. Yeah.
by the radiation effect. There is any example in our centers, sir?
So that I need to check and then I can confirm to you. But we have the models that you can incorporate for simulating the radiation effects.
Okay.
The
Next,
day the project I have to select, I have to like search, then only I can confirm to you.
okay, sir. Regarding to the mesh, you have shown the different types of machines are there available. So normally we give in terms of meshing as an 0.01 or 0.05 in terms of region wise or materials. Uh, what we have shown in the structure means device structure editor in the device editor. What is
Okay.
what makes the difference if you use a different mesh types means in terms of you use a rectangular square triangle. What difference will
So,
be there?
so difference in the shape, right? The rectangle, cuboid, this one.
So we are using different types of shapes means, so there will be any change in the output response?
No, sir. Like, sir, I cannot comment on the shape of the devices. So it actually depend upon
No,
the
no,
application
I'm
that you
not.
have
I'm
to
not
work.
ask.
But a
I'm not.
finer the mesh, you will get the more accurate result.
No, sir. I am saying that if you are using different types of mesh, you
Okay.
have shown that we have any different types of mesh are there available, like in four types of meshes.
Yes, axis aligned and the boundary confined meshing.
No, no. In terms of an triangle shape, square shape, you have mentioned in
Yes, yes,
the
sir. Rectangle, cuboid, yeah, yeah. All
yeah.
these shapes we have.
Uh, Means does it affects any output changes? If you are using, for example, I am using a normal mesh. Second time I am using a triangle mesh. Third time I am using a tetrahedral mesh. The fourth time I am using a cubic mesh. So does any effect on the output?
Yes, sir. It will definitely affect the accuracy of the devices.
Okay.
Yeah.
Regarding
Yes,
the
sir.
next question regarding to the in the GAN or high power devices, lot of issues are there, no sir, regarding to the error regarding to CV characteristics.
Yes, right.
Yeah. So means when you are getting a device is not converge in terms of CV characteristics. So what are the parameters it is required to vary or change to get to device to be converge?
So first thing is the we have to define the meshing perfect meshing value. Then we can go with the convergence. So this may be like issue in the convergence, and another things is the physical parameter that we are going to define. Sometimes the physical parameter is not directly accessible to the center's result, so that you have to write in the command file. So once we done with the accurate physical parameters, then I don't think you will find any convergences in the any kind of simulation.
No, we are getting normally IDBG, all the things are perfectly. The only the conversion issue is coming for only CV.
Okay.
Only for
Yes, sir.
CV.
You can let me know by the email as well. I will try to help you. So this is my contact details.
Okay,
Okay.
so
Yes,
what if
yes,
we
yes.
have to do a process simulation, sir? Like, what if we have to go for layout to process simulations and then device simulation? I need some insights on this.
Okay, so here you can see we have the workflow builder. This is the workbench, and here we can create. Let me create a process simulator. Yeah, here you can see we have added the SD. That is obviously for the structure creation by the geometrical method. Now, if you want to create generate a structure by using the fabrication steps like PS process, then we have to
Mhm.
add the process simulation. Let me add the tool.
Yeah, exactly. But before that, I need to know like how see there's a tool called structure editor, but there is
Yeah, right.
another tool called layout editor. So I need to know how the simulation goes from layout editor to S process. Like before S process, we need to know the insights on layout editor.
Like, sir, if you're going to create any kind of devices, then I
Mhm.
think you know their functions, like their materials, their exact coordinate point. Then then only you can create a structure by using the layout builder. And once you're done with the layout builder, then you can integrate. Integration is very similar. Like you can go with the structure editor here, and
Mhm.
at the right side you can add the process simulator this way.
Yeah, but
Then
sir,
it
let's
will
suppose
take
that.
the input
Mhm.
from the yes, it will take the
let's
output from
suppose
the SD into the process.
let's suppose I get some experimental data for device data from the foundry or something, okay? And I need to
Okay.
incorporate those in our simulations. So let's suppose if we have 4HSIC devices, more than one. Let's suppose we have 50 devices, and we need to connect all the devices in a diagonally or some kind of a layout structure, right? So how do we proceed from layout to S process simulations?
So regarding this, I will check after the session and then I can confirm to you.
Okay, maybe I'll give you a
Yeah, sure.
ping
You,
or something on the
yeah,
mail.
you,
Okay.
Yeah,
Good
so
afternoon,
this
sir.
is my point idea.
Sir,
Yeah, please. Yes, please.
sir, good afternoon.
How we'll get a
I want to
recorded
know one
recorded
thing.
video of
Hello,
today's session?
hello,
Yes, sir,
sir.
please go ahead.
Good afternoon. I want to know one thing that you have shown that the breakdown voltage, how it can be generated. I want to know
Yes, right.
the function, whatever you have defined in the sdevice.cmd file. That means how you have
Yes,
generated
right.
that BV file. That is my question.
So let me show you. This is the power. This is the SIC. So here you can see how we have the diode and we have
Hmm.
added the RBV characteristics.
Okay. So these files you have taken from Sentaurus Winjard
No, sir.
or
Actually, in the wizards, here you can see.
uh,
Let me show the wizards.
actually I am not getting in my computer. Actually, in my Sentaurus in my Sentaurus platform, Sentaurus Winjard is not available. So is
Okay.
there any
So which
other way
version
to
of
get?
this version of Sentaurus ticket you are using, sir? Can you let me know?
I have to check actually. I have not seen the
Okay.
version. I cannot remember. That's why.
Actually, sir, I am using the latest version, 2025.
No, no, it is not my latest version. It is not my latest
Okay.
version.
Okay, sir. No, so you can check and you can let me know.
So how to
Okay, so
implement this,
I
sir?
will try to.
Same thing.
Yeah.
only one thing you
Yes.
tell me that what function you have defined in the S device file. Can you open this input file? Yes, comment section.
Yes.
Can you
Yes.
open
Yes.
the
Yes.
comment
Sir.
section?
Yes. 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 Let me open. Yeah. Here you can see. So first you have to
Okay.
define the file that we are going to take from the either process
Yes.
simulator, either the or SDE. So once you've done,
Mhm.
you can go with the physics models that we are going to incorporate.
Depends upon the physics section.
Yes, right.
Mm. Plotting section is same as well as your S
Yes, yes,
device.cmd
yes,
file.
yes,
Plotting
right.
section is same.
I
Mm.
for IV and BV, the plotting is same. Only we have
Plotting is
changed it
same.
in the
Only the
physics
physics are
models.
changing. Physics section is
Yes,
changing.
yes, right.
Hello, good evening, sir.
Good.
Yes, good evening.
Yeah, good evening, sir. Thank you for your nice
Yes, yes,
presentation. Sir, I want to ask
yeah.
that, sir, what is the process of the optical simulation? Just, matlab, if I designed a SPAD device, single photon avalanche diode, that is basically a photo detector. So
Okay.
how can you, how can I give the command, basically in S device for the optical simulation to find the
So
probability
like
of
if you,
the,
yeah,
to
if
find the
you know
probability
the
of the
command, then
photon
you can go.
absorption?
Yeah.
Yeah,
Okay. Like if you know the command for any devices, then you can easily select the S divide, go to the edit option, go to the command, and you can write your script. If you are not aware about any scripting engine, so first you have to go with the manuals, and in the manuals it will help you to help you to define how we are going to define the materials, how we are defining the physics models. So that manual will help you to define a particular physics and plotting data. And once you've done, you can go with the simulation results. And if you are like aware, then you can go with the read command option as well. And if
okay.
any
Sir, there is
workflow is
another question,
directly
sir. How
available
will I?
in the yes result, yeah,
Yeah, yeah, sir. Yeah. That I know. Yeah, sir. Thank you, sir. Second question is about how will we decide the meshing? At what parameter, at what physics, what is the size of the machine? How we will we decide in the basically when we draw the structure in the SDE. It is depend on the dimension of the device that we usually take, or it depend on
yes,
some physics. Yeah,
it also depend upon the dimension of the devices that you are going to create, and it also depend upon the physics model that you are going to incorporate. So the final mesh you will create, you will get more accurate result, and also it will take more time.
okay.
Good afternoon, sir.
Thank you, thank you.
Excuse me, sir.
Yes, please.
Can we do the same procedure for other wideband materials like GaN and gallium oxide, etc.?
Yes, yes. So the process are same for any kind of materials,
Okay, sir. Thank you,
either
sir.
for the gallium nitride,
Sir,
silicon
I have a
carbide.
one doubt again.
Yes.
Sir, when
Sir,
it's
for HEMT device construction, do you have any reference to learn or build, sir?
Actually, here you can see I have already created some of the HEMT devices. So let me check. Now,
In the one regarding to the hemtol, sir, can you go for an hetero once?
which one, sir?
Hetero, hetero, the above one,
Heterostacker.
the
Okay,
hetero.
this one.
Yeah, yeah. In hetero, we have an that breakdown analysis and DC characteristics and RF characteristics, no, sir.
Yes,
Why
right.
this the same code is not being utilized for means if you are using an that same RF code for an other hem. So why it is not going to link?
So I don't think it will create any kind of issue.
No,
But
sir. We are
if
getting
you
the
are
same
facing
reason.
any issue, so
No.
what kind of like issue you are facing? So while you
For
are entering the
example,
same code,
yeah. For example, can you open the hem RF?
yeah, this one.
Can you open the SD this one? SD visual. Uh, in the down section. Coming to the down section.
Yeah, please let me.
See the from the system onwards, the system is there. No, the system is regarding to the calculation with the impact resistance.
Yes, right. This is for
So
the RF.
uh, RF calculation. The same thing if you're going down means only the thing is this is what we are the plot section will be same for similar all the end devices.
No, sir.
So if
Actually, we have to. Yeah, sir. Actually, I have to check the physics parameter that we are going to define for any other devices.
mm, okay, sir.
Sir, I have to check without. Yeah.
sir, how to do S process, sir?
Sir, sir, there is a question regarding the noise
Hello.
resistance for the GAN hem. Can we include the MOSFET simulation process, like the noise simulation of the MOSFET and similarly also GAN hem?
Yes, noise effect you can easily simulate for the MOSFET devices as well.
Like there is one question, one example given in the CMOS case or analog like that. Can you check
Sir,
the
your voice is very low. I'm not getting your point.
Sir, good evening,
am
sir.
I audible, sir?
For one more question.
Audible. Hello.
Hello.
Am I audible, sir, now?
Sir, please ask one by one. Yeah, please.
Yeah, now audible. Am I, sir, audible?
Yes, 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 yes. Yes, sir,
Noise,
please tell me.
noise analysis for the GAN hem.
Okay.
So if I include various parameter and finding out the like noise figure and all that thing. So how we can define that thing, sir, in case of this?
Hello. Good evening, sir.
Sir, noise is also possible in this Sentaurus TCAD. You can
One last
easily
question.
design by the S wizards, and you can also write the command by using the command option.
Hello.
If you know the script, then you can go with the command option. And you can also take the help from the manual section as well. So manual will
Sir,
definitely help you. Till,
and
yeah.
one more point also, sir. How we can define the uh, thermo resistance for the EG device?
So you want to define the thermal resistance of any particular devices, right?
Basically in the
Yeah.
GAN,
So you
EG,
can
in GAN the
in
EG,
in
the
any devices you can just right click, go to the parameter. You can define the here you can define the parameter thermal resistance, define their value, you can select the OK. Then that value will apply in the devices.
that for
Hello.
the thermal
Sir, if the
define.
thermal resistance is variable of the temperature, how can we define it in the code? Like in
So
the hand structure, we are defining. Yeah.
yeah, so different like thermal resistance only we can define. You can go with the least one. You can see we have the least where you can define number of lists like 5 point or some iteration like from 0 to 5 or some this kind of where you can define and then you can go with this simulation.
Sir, one more question.
Can we also vary the temperature for this, sir?
I optimize the
Yes, temperature variation
At,
is also
for
possible.
at different temperature, like I'm doing the self-heating effect or by defining the thermal resistance of the devices.
Yes.
So,
Variation of the
can,
temperature is also possible.
so how can we do that, sir?
Yeah, ma'am, actually we have the time limitation, so just you can drop a mail to me. I will try to
Oh,
help
yeah,
you.
yeah, definitely.
Yeah.
Thank you.
Okay.
hello.
Yes, please.
Yeah, good evening. Sir, one last question. If I optimize the graded head layers in any device, basically like the if you talk about the graded hem, so there is a mole fraction. Basically, graded layers is basically when we tune the band gap by changing the different mole fractions.
Right.
So how will we change into the S device? What are the parameters that we give? If I have to optimize the different layers in SDE or directly can we do into the S device code directly? Through which they
You
can,
can
yeah.
you can also go with the directly with the SDI port, and you can also go with the layer by layer as well.
Sir, in specific that layer, or we do the overall the
You can
physics
go for
section.
full structure.
Okay.
Sir, how is S device different from S process, sir?
Actually, yes, device is basically based on the geometrical method. Like layer by layer structure, we are going to create and we are selecting the materials. We are not defining any temperature variation, any dose value. But if you want to create a structure for the better accuracy, then you can go with the process simulation. Because in the process simulation, we are depositing the material by using the process method, like the deposition, oxidation, etching, implantation. So the accuracy will be like higher than the ES device.
Okay. Thank you, sir.
Yeah.
So I have a question one. When I change the my barrier material to algan to ingan, is I mean I'm unable to get the 2 there. So should I change any physics model there?
Pardon, sir, repeat again.
So when I change my my barrier in hem from algan to ingan, so
Okay.
I'm unable to get 2 there. So should I change any physics model
Unable to
or
get unable to get what parameter?
2
2DG, 2DG.
2
Okay, no, 2 DEG, right.
So I'm unable to get 2 deck. So is there any change? I mean, should I change the physics model or
Yeah, definitely we have to change the physics.
so?
If you are
But
changing the material, yeah.
Basically,
when
you have
I
to add
mean,
the piezoelectric polarization model.
yeah, physioelectric polarization model I included. But even though I'm unable to get there, so what should I do to? I mean, rectify that?
So actually, I haven't
So
simulated
basically, you
this kind
have
of
to add the
devices.
trap charge assisted model. That I have also worked on this, but you have to add the trap charge assisted model basically for getting the charge into the channel that is basically the 2DG negative charge.
Okay, I will try.
So if anyone has any query, they can let us know, and you can also get back to us by the email and the numbers after this session. So if there is no query, I think we need to conclude this session. So I would like to thanks all the
Sir,
participants who joined
one
us.
thing, one
Yes,
thing.
please.
Sir, can we get the video recordings of the session?
Yes, definitely. We will provide the video recording of this session after the complete of this
So
session.
kindly provide
We
us.
will share. Yeah, we will share with the mail and the WhatsApp group as well.
Okay, sir. Thank you. Thank you.
Thank you very
Yeah,
much, sir,
okay, thank
for
you,
your
sir.
kind
Okay,
presentation.
thank you.
Sir, can
Yeah,
you
so I
please
would,
again tell
yes,
when will be
please.
this session like this session, sir?
We will definitely let you know.
Sir, is there any dummy version of the Centaurus and Quantum 4K and all?
Actually, I don't have any idea about the Demi version.
Sir, from
Okay,
where
sir.
can
Thank
we
you.
learn this S process, sir?
Yes, please.
Like now we have teached about S device and S visual motor. So from where can we learn this S process, sir?
Yeah, manual is there that will help you to go with the process in design device, in design structure editor. And in the next session, we will like try to focus on the S process as well.
Yes, sir. Thank you, sir.
Yeah, thank you so much. Thank you. So I would like to thank all the participants who joined us today. So your active participant make this webinar meaningful and impactful. So thank you once again and have a great day.